Alright, so in this video I'm gonna be explaining another important paper with the title Descriptive Kernel Convolution Network with Improved Random Walk Kernel. So this ACM paper in 2024. Even if most of the valuable papers are those papers who are rejected. They are rejected just because maybe the reviewers have not understood that. But I've seen several wonderful papers that are rejected, and but they have been accepted in the future conferences. But this paper is very nice. Graph kernels are designed to measure similarity on a pair of graphs. However, they produce fixed handcrafted features. This reference derived the first neural network that outputs random walk kernel similarity scores between input graph and hidden learnable path-like graphs. So there are many ways to create graph kernel, like graph kernel, the WL kernel, like graphlet kernel. There are many ways to create a random walk kernel, but of course we should care about the computational complexity of that. Some of them are order of cubic complexity in the NN, number of nodes. Some of them are NP hard, so we try to avoid it, even avoid the approximation of that. But we can use graph kernel for many different reasons. For example, let H be a representation of node V at Tth layer where M sub T is a number of learnable kernels. So let these W1, Wm denote a series of learnable hidden graphs in the Tth layer. The subgraph around node V can be represented like this. So K is the graph kernel. Because we want to compute the similarity between two graphs. So if we want to kernel of two graphs, one of them may be the subgraph around a vertex. But the other one is just some, they should be learned, they are hidden. You can consider it as a latent variable, like some filters that you do in convolutional neural network. But when you go to graphs, then we have something like, of course, there is a paper in 2025 that was the first idea was in 2020, it was called Graph Kernel Neural Network. Excellent paper by Michael Bronstein. And this is similar to that they do node embedding and then pooling of these node embedding for graph classification. But the way that they create node features is interesting for me, because they create a vector for each of them. For example, the ICE entry, they defined it using two kernels. Of course, two different versions of their model. One of them WL kernel, the other one graphlet kernel. But doesn't matter. For each entry of this vector, they say what is the subgraph around that node, and then they compare it with the learnable filters. So once they do that, this is the representation for ICE entry. So it goes here. So here is a different, it's very similar to that idea, but let's carry on. So learning descriptive features. KCN were originally proposed for supervised learning As such, the learned hidden graphs are discriminative for classification tasks. We claim that the KCN model can be paired with an unsupervised loss and used to generate descriptive hidden graphs instead, which is not achieved by existing graph neural networks. Given the output of a single layer KCN model is the similarity scores to each hidden scores, one can train KCN by maximizing the total similarity score. So the unsupervised objective is like this. Then they revisited this random walk kernel. And so this is the issues of adaptive random walk kernel to KCN, because the original random walk kernel is designed for labeled graphs and cannot handle graphs with continuous node attributes that KCN are often used for. To that end, these authors in this reference proposed an extension of that. So they propose to compute the revised random walk kernel like this. So it computes walks with length exactly t. So this SS transpose applies reweighting to A such that the ij's element becomes Sij. And this one is equal to number of length t walks from pair of nodes I to pair of nodes j. So color matching random walks with efficient computation. So they address these two issues that we discussed, and this is the reformulation toward efficient computation. So this is their algorithm, fast color matching random walk. Given your graph G and maximum step T, then you return these two values. And they talked with the connections with graph neural networks. But these are the data sets they use for graph anomaly detection as well as graph classification.